So, bonjour, good morning. Thank you for joining us today. I'm Renaud Seigneuric, Attaché for Science and Technology at the Embassy of France in the US. I'm assisted by Linda Amishi, Deputy. She will take over on Wednesday. We are based in Houston, the energy capital of the world that may also become the world capital of the energy transition. Before we start, we'd like to thank our co-organizers, the Heart Research Institute, in particular, Larry McKinney and his colleagues. They will host Wednesday's session on water. Christelle Roger from MySeco, she will focus on biomimicry for water management on Wednesday. Kalina Raskin from CBios, she will provide us with a biomimicry perspective today and on Friday, when we will be talking about resilience. Let's have a special thought to our colleagues from Louisiana, which had to decline participation due to the Hurricane Ida. We wish them to recover very soon. And now we have to monitor Tropical Storm Nicholas heading up the Texas coast. So let's hope that we all, and also the organization of these French-American Innovation Days, will not be too impacted. A quick word on the International Union for Conservation of Nature, IUCN. Its World Congress ended in Marseille this weekend. They urged governments to implement a nature-based recovery from this pandemic and to urgently address the interlinked climate and biodiversity crisis. They also came up with the so-called Marseille Manifesto, aiming to capture key messages, including we are reaching a tipping point. We need to conserve nature to maintain our own resilience, and we need to implement nature-based solutions. Kalina and Christelle were at the Biomim Expo during this Congress, and I hope we will learn more about this during the 3 days. Without further ado, I'm very pleased to give the floor to Mireille Guyader. She was the first attaché for science and technology in Los Angeles, then served as the INSERM representative in Washington, DC, then worked at the IRD. Back to the service of science and technology, she's now serving as our new counselor. Mireille, the floor is yours.
Thank you, Renaud. Mesdames et messieurs, ladies and gentlemen, I am Mireille Guyader, scientific counselor and head of the Office for Science and Technology, a team of 22 members, including professors, senior researchers, and engineers working at the Embassy of France in Washington, DC, and in 6 consulates offices, including the office in Houston. Our general mission is to promote bilateral partnerships in science and technology, and to foster exchanges between French and American researchers and their organizations. With this goal in mind, it is a real pleasure for me to welcome all of you at these French-American Innovation Days on physical sciences and engineering solutions for the environment, green and blue in short. Due to possible Zoom fatigue, my speech will be short, and I know you didn't came today to listen to me. So first, I would like to mention that this virtual conference addresses 3 main topics. The first is innovation in energy today. On Wednesday, it will be on water and the environment, and on Friday on resilience in the built environment. There are also 2 side events, a biomimicry innovation workshop, which will be held tomorrow, and a Café des Sciences on bio-inspired design and adaptive morphology, organized by our colleagues in Chicago on the 16th of September. All these events are in the intersection of science, technology, and innovation with a focus on biomimicry. So what is biomimicry? Well, you will hear about that, and you have experts that will provide you with definitions, examples, and perspectives. But in essence, biomimicry is an approach that learns from and mimics strategies used by nature and its 3.8 billion of years of evolution, a real proven R&D ecosystem, if you will. The second point I wanted to make is that a few months ago, the Paris Agreement was celebrated in France and also throughout the United States, thanks to President Biden, including by our Service for Science and Technology. Wildfires, heat domes, hurricanes, including Halide, just a couple of days ago, leaving more than 1 million people without power, are just a few of the reminders of our close connection to the environment and how worrisome and frequent these events tend to be now. Obviously, the environment is also part of the equation we are trying to solve as scientists, engineers, and entrepreneurs. Taking into account the environment and having a more holistic approach is challenging, but it is also a highly needed paradigm shift. This is the spirit behind these French-American Innovation Days on physical sciences and engineering solutions for the environment, which is directly related to at least 3 of the Sustainable Development Goals: clean and water and sanitation, affordable and clean energy, and sustainable cities and communities. It is also linked indirectly to 7 others goals. Without further ado, it is my pleasure to give the floor to Juliana Garaizar, the head of Iucn Incubator and Vice President of Innovation for Greentown Labs in Houston. She will moderate this session dedicated to innovation and energy that get together researchers and engineers from France and the United States. Wishing you all a very fruitful exchanges. I hope you will initiate future collaborations between our 2 countries. And I leave the floor now to Juliana. Thank you for your attention.
Merci, and welcome to Houston. Thank you everybody for having me here in this French-American Innovation Day first day. And I'm Juliana Garaizar, head of the Greentown Labs Incubator and VP of Innovation. And I'm really, really glad to be here moderating this first day for you. So the day is going to take 2 parts. So we're going to have, before the break, the first topic is going to be on energy production and harvesting. We're going to have 3 presenters, 10 minutes presenting per each, and then 10 minutes Q&A. And after the break, we're going to talk about energy efficiency and sustainability. But before that, I'm glad to give you a little bit of an overview about Greentown Labs and the state of climate tech. So thank you so much for leaving me the time to do that. I'm going to now share my screen. Let me know if you can see it. Okay, I'm going to speak about Greentown Labs and the state of climate tech. So Greentown Labs, for those who don't know, is the largest climate tech incubator in North America. We were founded in 2011 outside of Boston, Massachusetts, in Somerville. And now we have 4 buildings, 3 in Somerville and 1 in Houston that we just opened on Earth Day. We have a total of 140,000 square feet of office, community space, and what we call prototyping space. And that's why we call ourselves Greentown Labs. Our main focus is climate tech. So really solving climate change challenges. And what do we mean by climate tech? Many of you already know that climate tech is real. So that was proven, and it's already here. So not only we need to limit and mitigate the impacts of climate change through several of these industries, as you can see here: electricity, agtech and water, buildings, transportation, manufacturing, but also we need to mitigate the impacts of climate change that are already here. And for that, we use resilience technologies that prepare people, communities, and infrastructure for the climate change impact. And we can see quite a lot of it, at least in Houston this week. So as you can see in Greentown Labs, we have quite a lot of startups that are in those spaces for energy, but also agtech and water, energy efficient manufacturing, transportation and buildings, and the resilient space. Because we've been doing this for 10 years. And that's why, just a second, I'm going to tell you a little bit more about Greentown by the numbers. In the headquarters in Boston, we have a campus of 100,000 square feet, and we have already incubated more than 350 companies over 10 years. 1.6 billion in economic impact was created in the region of Boston, and 6,500 jobs were created. But the number I'm most proud of here is the 88% survival rate. That's very high compared to many other incubators and accelerators. And of course, it's also because we get a lot of good candidates in. As you can see in the bottom, the member growth is doubling every 2.5 years, and that's when we would get actually a new building. And where are we fitting in the startup journey? Normally, our companies come from a university. It could be from the MIT in Boston or from Rice or U of H here in Houston. They go through a course that could be like Energy Ventures course. Then they decide to put together a business plan. They go through a business plan competition, like maybe the Rice business plan. They win some money. After that, they come to an acceleration program like Mass Challenge or Y Combinator. And that's when they get seed funds and they can get to Greentown Labs. We are not taking any equity because we think that many of our companies come from accelerators, and that's why we don't want to get another chunk of money. In general, our companies stay for 2 years. On average, they come with 2 people and they leave with 10 to 15 employees. And we also help them raise their Series A when they're ready for scale. We also help them with prototyping, pilots, small scale manufacturing. One of the very big questions everybody asks us is why we decided to move to Houston. Well, Houston is the global energy capital, and we really believe that they needed to play a very big role in the energy transition. We also had quite a few committed champions, the mayor of Houston being one, but of course we have a lot of sponsors like Shell, Chevron, and many others, NG too, that have a very strong presence in Houston. We felt that we were filling a gap because there was no clean tech, climate tech specific convener in Houston, but there was still a very burgeoning startup ecosystem with a lot of newcomers like Mass Challenge, Generator, and all that. So we decided to open our first building in Houston that's going to cater for more than 50 startups, 40,000 square feet, and the mayor, of course, being our biggest champion. He wrote a letter to our board in Boston to make sure that we were expanding, and we did our first expansion to Houston because of him. Here he is doing the grand opening. And not only we had the mayor, we also were able to have the Secretary of Energy's first visit outside of Washington, D.C. on May 28th. So that really indicates the importance that Houston is taking in the energy transition and Greentown Labs as a catalyst for it. So after we open, it's been 4 months already after Earth Day on April 22nd. We are so pleased to say that we are now at 43 members. Oh, that's how we call our startups. And, every 2 weeks, we have at least 1 new member coming in. So really, really growing at a very nice pace. And these are all the corporate partners that we have engaged both in Boston and Houston. And our companies are not the typical software startups. They are hardware companies that need a lot more help and really need these engagements with the corporation. Why? Because for us, the path to scale is a little longer, and it requires not only investment, but in many cases, we do quite a lot more things with our corporations. We do a lot of pilots, we do project collaborations, they become customers, they do R&D contracts, commercialization agreement, joint ventures. So success is a little different for us compared to the software companies that you can find in Silicon Valley. So I'm going to talk a little bit now about the state of climate tech after, in 2021, where a lot of things really changed. What did really change is, of course, that we took very bold steps at climate leadership. At federal level, the Biden administration pledged to cut greenhouse emissions by half by 2030, which is really aggressive, 100% clean energy by 2035, net zero emission by 2050, and of course, the 2 trillion climate focused infrastructure plan. That's going to require a lot of innovation, because many of these dollars are going to be invested in technologies that are not even invented yet. So in our case, we have a lot of corporate investors for Greentown Labs in both Houston and Boston. We have quite a lot of corporate VC funds that get to invest in our companies. These are a few examples, but we are not only talking about corporate investing, we're going to see many more other sectors investing. These are the hot, I would say, areas that are really critical for innovation and that many of our corporate VCs are investing in: energy storage, carbon capture, or what we call generically carbon tech, circularity or recycling of anything, but of course plastics is very big in Houston, offshore wind, ag tech, of course agriculture emits a lot of greenhouse gases, hydrogen, also another very hot sector for Houston, and buildings, and actually in many areas, building overcome transportation in terms of greenhouse emissions. These are some of the early stage investors that are also investing in climate tech. Many of them are actually partners of Greentown Labs Houston, or even founding partners for Greentown. And we also have quite a lot of government support, NYSERDA being one of the most obvious ones for Houston and for Greentown and MassDC, but also ARPA-E, Berkeley Lab, and Carl Seed in between others. But there are other bigger funds like the Green Climate Fund, BlackRock, Amazon, the Bar Foundation, Unilever, Microsoft, and Bezos are funds that are really stepping it up in terms of investing in climate tech. These are some of the examples of how, many of these Greentown Labs companies got investments. These are some of our most successful ones, and actually Syzygy Plasmonics is going to be our third presenter today. So one of the things we are very proud of, because we really thought that getting investors to our startups was key, was our investor program. Not only we have a dedicated investor newsletter and a deal flow digest that goes monthly, but we also create fundraising forums, investor speaker series, investor hours, and pitch opportunities. And what we call carbon tech are really critical areas of innovation. We really feel there's a huge market opportunity and there's a wide space of innovation. There's been a lot of carbon capture, but not a lot of what we do with that carbon once we captured it. And that's why we decided to go a step further. And at Greentown Labs, we decided to bring together a carbon tech ecosystem with this C2V, or carbon to value initiative. We decided to create a carbon to value council and carbon tech leadership council that is made of governments, but also of corporations and of course of startups. This carbon to value initiative started in 2021 with its first cohort, where we also have a company from Houston, Cemvita Factory, but it's actually going to take 3 years, which is not normal for an acceleration program, but that really emphasizes the importance of carbon tech. The 4 pillars of climate action for us are not only technology, where we have a lot at Greentown, but also finance. We really believe that climate tech revolutions offers economic opportunities and diverse capital sources for innovation and are key to tackling climate change. Policy, of course, we know that this impacts a lot, but we don't have to forget the climate justice. At the end of the day, we know that climate change impacts most the underserved communities, and we need to require, and we really require to address both problems at the same time. Back to you. Thank you very much. And now, without further ado, we're going to pass to the second part of this event, starting with the first. So I'm going to stop sharing. We're going to start with the first presentation that is already ready for today. We're going to have the first presenter is actually Alper Erturk, is a professor at Georgia Tech, is going to talk about energy harvesting from diversions, elastic acoustic waves, and fluid structure interactions. Back to you. Alper, are you there? Are you able to hear him?
Alper, I think your microphone is mute.
Sorry, I was apparently still on mute. Sorry about that. So yeah, I hope you can see my screen.
Yes.
Okay. So thanks again for the opportunity. You know, I'm a professor in mechanical engineering at Georgia Tech, so I come from a more academic perspective on using leveraging different sources of, especially non-conventional sources of renewable energy, such as vibrations, fluid structure interactions at smaller scale, and so on. So hopefully it gives an alternative perspective to these other various sources of energy that can be leveraged, especially for low power electricity generation. So we'll talk about like the leveraging of direct vibrations, fluid structure interaction, and so on. So the overall goal in energy harvesting, whether it's solar energy, thermal energy, or motion energy, the goal is to try to come up with energy autonomous, or what we call self-powered devices or systems. And in that regard, like obviously you have very mature technologies. So let me try to see if I can get my pointer. Yeah, mature technology is just like solar cells. You can find flexible or rigid solar cells very easily off the shelf. But what we're going to talk about, especially is for low power electricity generation, for enabling wireless electronic devices such as sensors and other monitoring devices used in applications such as active and passive monitoring in structures or biological systems. I put this graph to give you an overall context in terms of the power levels of different approaches, and also in comparison to like a compact devices or batteries. So power density means in a given energy harvesting system or a device, how much power per device volume. For instance, if we are talking about a solar panel, it will be how much power you can generate with it divided by the volume of the panel, and so on. So that vertical axis is that, and it's in logarithmic scale, and the horizontal axis is how much voltage you can directly generate from that to charge a storage component like a battery, and so on. So we'll especially talk about piezoelectricity today to use in various dynamical systems problems to harvest energy from various sources. And again, I'm hoping that it may give you a different perspective compared to like relatively more conventional stuff. One of the interesting stuff about piezoelectricity, although it's low power compared to solar and so on, first of all, you can generate electricity from motion even in the absence of sunlight. Another advantage is that, or a positive aspect, is the power density levels can be comparable to those of like lithium-based batteries, just like in your smartphones and so on. So that's why the dream is ultimately, can we one day try to make use of, for instance, like while we are walking, would it be possible to use some piezoelectric elements, convert that motion energy on variable components into electricity to come up with like self-powered electronic components, like variable devices. And in a nutshell, like in this short presentation, just to mention, not to go into technical details, but obviously piezoelectricity doesn't happen in all materials. So it has to be a special kind of material, and that comes from like an atomistic level of arrangement. For instance, even silicon dioxide, which is natural quartz, has piezoelectricity because you have to have this non-center symmetric arrangement to have some polarization in response to deformation. So what we try to do, and the reason we try to do this low power energy harvesting, is for applications such as the Internet of Things cases. Like you could have variable electronic components, you could have smart homes. Would it be possible again, like to use various sources of energy therein? If you can think of like, if you want to think of a direct application, it doesn't have to be too futuristic, like in the Internet of Things, where we will be connected to many sensors in the near future, like tens or hundreds of them. Today's application, one of the applications of energy harvesting, for instance, is structural health monitoring in modern bridges, just like this one, or I previously worked on again, monitoring in helicopter structures. So the whole idea is to use wireless sensors in such structures, is to do is to minimize the downtime for maintenance purposes. But then the problem becomes, if you use batteries for those sensors, you have to go and do maintenance for the batteries. So that still is an issue. Would it be possible to harvest vibrations, flow energy, and so on? Here's where the challenge becomes. Unlike solar energy, vibrational energy, motion energy, its signature is very much case and application dependent. Even for like when we try to do the quantification of vibrational energy in human walking, the frequency of oscillation may change, you know, when you're walking at a lower speed, faster speed. So when you design a harvester that will leverage the concept of resonance that you may not be familiar at all, you can design at a certain frequency. The moment you change, your speed changes, you know, you cannot harvest any power output. So that's why we leverage concepts from dynamical systems. We deliberately introduce, for instance, I will show only one of these videos. It's a bistable structure. Normally, you don't want chaos and large complexities in structures, but in energy harvesting, we leverage them. And these concepts we introduced first, now they're being used in microscopic like MEMS devices to have broadband or wideband devices. Other applications, and I will stop probably within a minute, so would be in cases where you don't have direct persistent vibrational energy, but you may have bursts of waves. I don't know if you ever heard of metamaterials or phonemic crystals. Meta means beyond in Greek, so we try to leverage in that research domain concepts, you know, by designing structures that will give you properties beyond ordinary properties of material, like negative refractive index, band gaps, and so on. So, for instance, what is the relation to energy harvesting? If you try to harvest acoustic energy, like a sound energy, when you're talking, that's a very low intensity. But we borrow those ideas from metamaterials, like making a lens. Can you concentrate the energy and then harvest it? So a nanowatt level energy can go to, let's say, microwatt, and you can start to do something with it for wireless sensors. After this, I will stop. Other applications involve, you know, I keep hearing biomimicry and bioinspiration. This is a quick example of bio-inspired robotic fish domains, still using piezoelectricity we use in our lab. So you can use piezoelectricity is two-way coupling. So you can have mechanical input, electrical output, electrical input, mechanical output. So you can make underwater sensors. There could be multifunctional swimmers. They can both swim, and at the same time, at times they are not swimming, they can make use of flow energy. And same with like hydroelastic energy, like in response to, you know, flow input, you can generate electricity. So you don't have to have direct vibrations. You can deliberately introduce some instabilities to generate electricity for low power applications. So with that, I stop, and I guess there will be maybe a question session. If there's any questions, I will be able to elaborate more on these. Thank you.
Thank you, Alper. Great presentation. For those attending, please make sure you get your Q&A either on the chat or on the Q&A. I'll also be sharing those. So the first question for me is, what are the challenges and limitations to this energy harvesting technology?
Yeah, so the fundamental issue is being this more application dependent, as opposed to putting solar panels on a building, which is very much mature technology. So that's why all these things are still under development stage. There is no company making these, let's say, piezo patch developing companies sell some prototypical devices that will work only for a specific application at a specific vibration frequency. That's why we're trying to expand with basic research in academia, we're trying to expand the range of frequencies we can leverage so that it doesn't have to be limited to a fixed frequency on an aircraft wing or in the shoe for variable devices. So that's a major challenge.
And do you have any other relevant applications or ongoing research?
Yeah, so for instance, for Air Force Office of Scientific Research, my own PhD was for them, and later on, like I had my own grants for vibration attenuation on flexible structures. So that's where we try to introduce some multifunctional concepts. Whereas we develop these metamaterials, metastructures, which are periodic structures that could be used in an aircraft wing for suppressing vibrations. So you can do something useful with that structural energy by converting that into electricity, so that it can charge some sensors in the aircraft wing. So it may sound like a very kind of like a, let's say, minimum power thing, why not use battery? But it is estimated that for a commercial aircraft, the lifetime maintenance cost can be as high as 20% of the initial cost of the aircraft. So that kind of autonomous systems can in the future enable minimization of such maintenance cost is the idea. And other applications we do for government labs is for inaccessible devices, just like in military purposes. Sometimes we have these devices that you don't want them to be electromagnetically interrogated. This is with Sandia National Labs. In a Faraday cage, you cannot send any RF power or any other power. So we can try to send vibrational waves through the structure, which is more of like a wireless power transfer, but using acoustic energy. So there's a number of things there.
the last question I have is, what is piezoelectric?
Yeah, piezo means to squeeze. So it is, I tried to show that with a small schematic. So not every material, obviously aluminum or steel is not piezoelectric, but like lead, zirconate, titanate, this was developed mid-century in the past year, especially after the Second World War. But even in the First World War times, like people knew that quartz, for instance, natural materials like quartz, they are piezoelectric, meaning their atomistic arrangement is in a way that, like, in response to deformation, there is a kind of like net polarization, and it adds up to something usable at the macroscopic level. So that's a special type of smart material, if you like.
Thank you. Very, very interesting. Okay, now we're going to go ahead with our second presenter for today, coming from the Université de Pau. Laurent Billon is going to talk about hydrogen production by artificial photosynthesis. So Laurent, whenever you're ready.
Okay. You can see my screen?
Yes, we can.
Perfect. Thank you so much. First of all, I would like to thank the organizer for their kind invitation. And I changed a little bit the title of my talk today, and just to explain to you what are the philosophy, or what is the philosophy of the group here in University of Pau and other countries. So today I just want to talk about bio-inspiration towards energy sustainable and independent bio-inspired territories. So most of you know that in nature we can find many interesting materials or living system, as butterfly wings, the self-cleaning surfaces of the lotus leaf, or the adhesion of the gecko leaf. But in all the cases, what is really interesting is we have some hierarchical organization of the matter, from the nanoscale here to the macroscopic scale. So it means the living species. And it's also the case in a gecko leaf here. So, and then what is quite interesting, in all the cases, you have a combination between the chemical nature of the material and the structuration of the material. And then finally, you have a hierarchical structuration from the nano, as I said, to the macroscopic scale. So from this, I would like to say expertise, or this evolution, we can use some specific materials. And here, it's a quite interesting material obtained by a very simple process. And then this material is not exactly a diatoms. Here you have an example of diatoms, but in the bottom, what do you have? It's a polymer film. But this polymer film is created by a specific process called breeze figure process. So it means when you breathe on a cold window during the winter, you have water droplet condensation. And due to the water droplet condensation, you can create some structuration of a film. And then it looks like a diatom. Why it's interesting and why this material inspired us a few years ago? Because with diatoms is an exoskeleton of algae. And then this exoskeleton is able to create some UV visible filtration, chemical filtration, and then the algae can make some photosynthesis. So what is quite interesting is the idea is to use such kind of structured film in order to mimic what's happened in algae or what's happened in different leaves. And then what is also quite interesting, if you look at the diatoms could be quite complex. So it means you can have a hierarchy, a strong degree of hierarchy from the nano to the micron scale. And then using what I said, the breeze figure process, it will be also possible to create polymer films with a macron porosity here. And in between the micron porosity, we are able to create some nano porosity. So it means we can mimic what's happened in the diatoms exoskeleton. So it means structuration from nano to the micron scale. And then recently, we were able also to create a 3-level of structuration from the micron scale, sub-micron scale, and nanoscale here. And then you have 3 levels of structuration in the materials. So it means, as in diatoms, we are able to use 3 levels of porosity in the materials. And then the idea came to mimic such structuration in order to develop artificial photosynthesis. So it means recently we got a European project. The name of the project is Scale, European School on Artificial Leaf. And the idea is to develop electrodes, structured electrodes, as I described, as the diatoms, but also to develop devices in order to produce some hydrogen, but also to make some solar fuels. So the main idea of the eScale project is bio-inspired by the nature of the catalyst. So it means we have to use some catalyst for water oxidation, and then I will be back to this aspect, and also to use carbon dioxide reduction in order to mimic what's happened in the leaf. In the leaf, you use CO2 plus water plus solar energy in order to make some sugar, in order to create some material for the leaf and for the tree. So here the idea is to use some bio-inspired catalyst, to use the bio-inspired process based on the breeze-figure process in order to create micron pores, and on the surface of the micron pores to create some catalyst deposition in order to mimic what's happened in a leaf. So here, if you look, this is a honeycomb fields with the micron porosity, and here, this is the chemical structuration of a leaf. So you have some cells here, eukaryote cells, and in the eukaryote cells, you have the chloroplast. And the chloroplast is the manufacturing of the natural photosynthesis. So here, definitively, the idea was to locate such bio-inspired catalyst inside the pores in order to mimic what's happened in a leaf. And then, with a consortium of colleagues in Europe, we proposed to develop such kind of devices. So it means the idea was to use solar energy driven device in order to create some electricity, and then on the anode to create what we call water oxidation. So it means you use the water, then you release some oxygen, and you use the protons to reduce the protons with the electricity in order to produce some green hydrogen, or to reduce the CO2 in order to create some solar fuels. And then recently, what is quite interesting, what we did with such electrodes, we were able to create some porous electrodes using very simple, very easy manufacturing techniques as the printing techniques. So it means the main idea of the eScale project is to use, I would like to say, cheap and abundant element the nature is able to use to create some stable and cheap and efficient catalyst using the molecular catalyst as we can find in the nature, and also to use very easy manufacturing process in order to create some devices. So here, the idea was to create some hydrogen and then to mimic what's happened in a leaf. So it means to harvest the solar cells and to harvest solar energy, and then to create some chemicals, solar fuels, hydrogen or solar fuels based on CO2. But the idea was also to go further, because the main idea was to develop new technology, but to check if this kind of new technology can be extrapolated, not at the lab scale, but can be used at the scale of a territory. So here the idea was to develop new low-cost technology, but also to create, due to the intermittency of the new energy, to store and then check how is it possible to store the energy and also to share the energy. So here the idea was to create an autonomy of the territory due to the new energy. The idea is it possible to mimic the leaf with a house, with a home, at home? So it means during the day to use the solar energy by a PV, a photovoltaic panel or an organic photovoltaic panel, but most of the time you are not at home. So it means you produce some energy and the energy is injected into the grid. So is it possible at the scale of the house to store the energy in a chemical form or in an electrochemical form with a battery, and then in the evening, in the active phase of the day, so in the evening and the night, when the people are coming back to home, is it possible to restitute this energy and also to fill the vehicle with hydrogen or electricity? And then here the idea was directly linked to bio-inspiration or what's happened in a tree. Why? Because as a the territory are made from highway as a trunk of the tree. And then the branch can be the national and the local road. And then at the end of this road, what do you have? You have some cluster of houses, but you have some isolated houses. So is it possible to use these houses or this cluster of houses in order to produce some energy, and then by solidarity to share the energy with the neighbor of the territory? And then it means, especially in France, you open a black box. So it means in terms of law, in terms of economy, in terms of social point of view, nobody has already treated this aspect. So it means here in the University of Pau, we create a cluster named Ensuite. So it means and then. And the name of the cluster is Sea, Text, and Sun. So it means the idea was to use sun, to use the water, and also text to define if it's possible to use the water and the sun in order to create energy and to share the energy, but at the local territories. So it means without a national company, just with your neighbor. And then what we did, we create a consortium with scientists in terms of material science. But most importantly, what we did, we introduced some economical aspect, we introduced some social aspect, and also some law aspect, private law and public law, in order to answer to this question. Is it possible really to create energy at home and then to sell the energy to your neighbor? And then it's quite an open question still in France. And then what is quite interesting, all these laboratories on social and humanity science merge and create a new lab, and the name of the lab is TREE. Okay. So the name and the goal and the inspiration of the Ensuite project is to have an holistic approach in order to tackle together the legal, the economic, and the social aspect with the technical aspect. And finally, what we have in mind is to create in the University of Pau an institute of desirable energy, and the name of this institute will be ID. Thank you so much.
Thank you. Very, very inspiring presentation, Laurent. So I have a couple of questions from our audience. So what kind of materials can be fabricated with these various porosites? Can you control the directionality and density of the pores with good reproducibility, and at what scale?
Yeah, good question. Yeah, it's definitely possible to direct the functionality inside the pores or to direct the functionality on the top of the film. So in the past, we published many papers where we were able to localize functionalities at the surface of the pores. Yeah, easy. Due to the process, we can.
The next question is, how will these technologies scale up and deliver massive quantities of products? Where will it hurt? Stability, manufacturing process, energy balance?
Yeah, it's quite difficult to answer to such a question. Definitely what we hope, okay, because the idea is to use catalysts. So actually the hydrogen generation, the green hydrogen generation using a panel, photovoltaic panels already exists. But most of the time you use some non-abundant and very expensive metals. And here in the project, the idea is to use abundant catalysts. And I didn't say, but the idea is also to be inspired by the structure of the chlorophyll. So if you look in nature, what you have just one metal active center. And this metal active center is surrounded by an organic or carbon-based ligand. And then definitely in the project, we mainly use such kind of catalyst in order to reduce the metallic impact and then the price onto the electrode. So we do not want to use fully metallic electrode, for example, even if we well known that up to now, the efficiency of such catalysts, such electrodes are much better than organometallic complex.
Okay, the last question I have is regarding this European project. How do you deal with IP when you have so many partners, and how long is this project going to last? How do you foresee what happens after the funding is gone?
Yeah, also a very interesting question. Okay, as all the country belongs to the European Union, what we have a consortium agreement at the beginning. And then depending on the inventors and the university of the inventors, we have to make some specific agreement between two universities if it's needed. But usually with the consortium agreement at a European level is enough to share or to have some single impact on intellectual property.
And do you have a sustainable plan for after the project is over?
Not yet, not yet. The project will be over in 2022. So, but not yet. Yeah.
Hopefully, you have a lot of good results so that you can keep on going.
Okay.
Well, thank you so much. So, speaking of catalysts, and a great one of our most successful Greentown Labs members is Syzygy Plasmonics, and now we're going to have Hossein, I'm going to try to pronounce it well, Robatjazi, from Syzygy Plasmonics. Could talk about catalysts, I hope.
Thank you so much for the introduction and also for the opportunity. I'm here today to briefly talk about our progress on using light to power chemical reactions and to provide a more sustainable alternative to traditional fuel-based, high temperature, high pressure, heterogeneous catalysis process. Toward this goal, cutting-edge research in nanophotonic, to a history of understanding in heterogeneous catalysis. And by doing this, we can enrich the surface chemistry of these plasmonic metal nanostructures that can strongly interact with photons at optical frequencies, and they can confine light at nanoscale to create a local environment that can drive chemical reactions with high efficiencies at milder operating conditions compared to traditional thermal-driven catalysis. And it turns out that using light to derive chemical reactions can offer some reactivity channel that can enhance the selectivity of the product in some cases, and also can improve the stability of chemical reactions. We have used this approach in the past to demonstrate sustainable light-driven chemistry for several environmentally and industrially relevant conditions, reactions. Here are some examples of my PhD work. For example, using earth-abundant plasmonic aluminum nanocrystals as an antenna to capture light, and then coating these aluminum nanocrystals with a layer of copper oxides or decorating their surface with small, tiny islands of iridium or palladium. We showed that it's possible to use light to mitigate anthropogenic carbon dioxide through selective hydrogenation of carbon dioxide. And also we can dissociate nitrous oxide into synthetic air. And it turns out that we can also use light to break a strong carbon fluorine bond here in the fluoromethane mother molecule, which is a smallest family of the HFC compounds. So using this photocatalysis technology at Syzygy Plasmonics, we are developing and pioneering unique photoreactor platforms that basically can replace heat from fossil fuels with light from renewable electricity to provide a sustainable and green approach for chemical and fuel manufacturing. On the path to commercialization, once this technology become realized, it has a potential to revolutionize chemical and energy industry, basically by reducing the energy cost and carbon dioxide emission associated with chemical manufacturing. This is in fact a perfect timing to use electrified photocatalysis for chemical manufacturing, because the cost of the renewable electricity is trending down, and the LED technologies are becoming more and more mature. And also the use of light for driving chemical reactions under milder condition provides a path to use cheaper raw materials, for example, using glass or quartz and aluminum instead of expensive high alloy steel in traditional reactors, which reduces the overall capital cost of making these photoreactors. In terms of going to market products, our primary focus is on smaller scale systems for hydrogen productions, for on-demand hydrogen productions, and our customers are from a range of smaller scale hydrogen consumers. For example, hydrogen fuel cells for hydrogen powered vehicles, and also for a smaller scale electronic industry and R&D groups. In terms of producing hydrogen from feedstocks, we have quite flexibility. We have developed approach to make sustainable and green hydrogen from different reactions, for example, from steam methane reforming, from dry methane reforming, and also from splitting ammonia. And we focus on three primary enabling technologies. First, we are making breakthrough innovation on design and developing efficient, scalable, and cost-effective photocatalysis here at Syzygy Plasmonics. We are partnering with the top LED manufacturer in the world to custom design and fabricate fully engineered LED system with highest energy efficiency, and also for maximum light absorption in our system based on the photo management strategy that we implement. We also design several generations of photoreactors and photoreformers for our processes. These photoreactors are modular. They can be used for different reactions. Here, for example, for hydrogen production, our photoreactor, you can see on the right side, the prototype of photoreactor contains an array of photoreactor banks, and each photoreactor bank consists of several smaller photoreactor cell where the reactions happens, and we can have as many as a photoreactor bank in the system, only limited by the size of the system, to basically achieve the productivity level that we want. In terms of technology development, over the past 3 years, we have been able to achieve more than 500,000 times increase in the productivity, starting from 2018, when we were producing a few milligrams of hydrogen per day from a microreactor system, to 2019, where we were able to produce several grams of hydrogen with the lab scale reactor, and in early 2021, we were able to produce several kg of hydrogen from our prototype pilot reactor with a 50% energy efficiency. So it's ready to go. Here is the data from our 2019 test. Using steam methane reforming as an example, you can see stable hydrogen production over the course of 100 hours of test. And the amount of hydrogen is 100 grams per day from our lab scale reactor, at the energy efficiency of above 30%, and conversion of the products of about 70% only in the single pass. And here you can see our prototype or artistic rendition of our future field trial system, which is capable of producing 200 kg of hydrogen per day, which is about this full tank of about 40 hydrogen-powered vehicles. So we are planning to make a fuel station, hydrogen fuel station, based on this system. And finally, in terms of price, the current price of the distributed hydrogen is about $60 to $20 per kg. And it's not only about the price of the hydrogen, but it's also about the danger of basically transporting compressed liquid hydrogen. And based on our techno-economic model, CCZ hydrogen can provide a zero emission hydrogen at lower cost. When the technology is mature, the cost of hydrogen that we provide is somewhere between $1 to $3. So with that, I would like to thank you again for the opportunity. I'll be happy to take any question.
Thank you, Hossein. So the big first question is, what does Syzygy mean?
It's a very good question. So Syzygy is a very catchy name. Is basically it's an alignment of the three celestial bodies, the sun, the moon, and another celestial body, which is typically sun. For us, it's defined as alignment of the energy, sustainability, and technology to basically shape the future of chemical manufacturing.
Beautiful. So what is the timeline of your product release?
So we are expecting by the end of this year, we are expecting to release our first pilot reactor, which has a capacity of about 5 kilograms of hydrogen per day. And by the end of 2022 or 2023, we are expecting to release our field trial system, which has a capacity of 200 kg of hydrogen per day. And after that, we're going to go to the growth phase, and we're going to basically expand our capacity or manufacturing capacity to reduce the cost of hydrogen and the cost of the system.
So how would you compare your technology with other competitive technologies?
The direct comparison is kind of difficult, but based on the modeling that our business team have been doing, our technology can provide hydrogen at a lower cost and lower emission compared to some competitive technologies, for example, the electrolysis of hydrogen or direct methane pyrolysis.
Okay, and what are the main factors contributed to the photocatalyst design?
So there are several aspects to the photocatalyst design, but there are really two main aspects. One is the optical properties of the catalyst, and the second one is the surface chemistry of the catalyst. In terms of optical properties of catalyst, it depends on what kind of light source you're using. You can use different optically active plasmonic metal nanostructures, and you can tune their size, shape, and other properties to basically tune the wavelength at which the most light absorption happens. And in terms of surface chemistry, as I said, like there's a history of heterogeneous catalysis, and we're trying to use those findings from the past to basically modify the surface chemistry of these optically active plasmonic nanostructure in different ways in terms of like, making nanostructures or nanoparticles that are in the form of like core shell nanoparticles or decorated with the smaller islands. In some cases, we are taking advantage of single atom catalysis. So we are basically creating atomic sites on the surface of our plasmonic nanostructure to achieve the efficiency and the reactivity that we want for the given reaction.
Perfect. Thank you so much. So I know that we now have a break before continuing with the second part of this day. Well, no, should we keep it to 10 minutes to be on schedule? I know that it was planned for 15, but we're 5 minutes late.
Yeah, fine. Let's go. Let's go for 10.
Yeah. Okay,
thank you.
Perfect. See you in 10 minutes.
See you there. And for the speakers, just of the next session, please show up 5 minutes before, so we have a chance to rehearse everything and check technical issues. Okay. See you in 10 minutes then.
Okay, are we ready to restart, Renaud?
We're ready, almost ready. We didn't rehearse for the share, but share screen thing. But otherwise, we can start. Let me check everybody's.
Sounds good. Okay, welcome to the second part of the day. So we're going to do the second topic now on energy efficiency and sustainability. First presentation is from Aditya Mohite from Rice University. Please, whenever you're ready, Aditya.
Yeah. Thank you, Juliana. Can you all see my screen?
Yes.
Okay, great. See if I can go and let me get my pointer. Yeah, good morning, everybody, and thank you so much, Renaud, for this invitation. And my sincere apologies for the delay in getting things to you. I've had some terrible time with family health last couple of months, but it's really an honor for me to talk here because of many reasons. In about 5 years of my career, I have about 50 publications with French researchers. In fact, if you look up my publication record, there is a French researcher on the list there. And so I have close ties with France. And of course, beyond just love for the country and the people, there's also tremendous respect and love for the science there. So thank you. And so today I want to tell you a little bit about the journey of halide perovskites. This is a new class of materials that has come out of nowhere. And it's been a destructive technology, especially for photovoltaic devices for solar cells. And in many ways, this is sort of a magical material because it has properties that that are really a dream for any material system. And so I want to sort of talk to you about this. I'll keep this a little broad without going into too much of detail and tell you a little bit about what we've done with this system. Okay, so before we get into this, I want to talk about in general from a perspective of what are the new next directions I think that are going to be relevant for us in this energy transition, which is of course clear that there's going to be one. If we are to make photovoltaic devices, then we have to consider making them with efficiencies which are close to 30%. Without that, it will not be competitive because really, if you look at this cost of electricity equation, which is on the right, the efficiency is in the denominator. And so by increasing the efficiency, you would drive down costs tremendously. And so for photovoltaic devices, I think that's whatever technology you're looking at, thermal photovoltaics or lightweight, I mean, generally speaking, you will have to have high efficiency devices. Another technology that's going to be really critical is solar to fuels. And I think, we had Hossein who spoke about this of conversion of the syngas reaction of generating hydrogen. And I'll give you one example where we are really about to start a company where we use perovskite solar cells to generate hydrogen through another way, which is water splitting. And so I'll talk about that. The third thing, which I think is going to be important, is powering the Internet of Things. We are in the technological revolution as well. And so we are going to need portable power. And so that's where photovoltaics will be useful. And finally, of course, solar energy to drive pumps for water desalination using reactors and things like this. That's going to be, of course, really important. So I think that these are this is my list of things that I think is going to be really relevant going forward. But of course, there's more things that can be added onto this. Okay, so whenever you talk about photovoltaics, you have to look at this chart, which is really maintained by National Renewable Energy Labs. This plots the efficiency as a function of years, and you will see all the different technologies for solar cells here. And what I want to, and of course, these yellow rectangles here are for the two highest efficiency cells that we have. This is gallium arsenide or 3,5 group based solar cells, and they have the highest efficiency, about 30%. But they are not really cost effective. They're cost prohibitive in many ways. And then, of course, you have silicon, which we find on roofs every day. And so they are at about 25%. Now, if you see what has happened, there's this concept about using, generation 3 solar cells, which refers specifically to materials where you can put them in solutions and do dirty chemistry and spin them using different methods on different, and any surface and create sort of photovoltaic devices like that. And so some of the examples were these dye-sensitized solar cells or organic solar cells. And you see that over 30 years, these efficiencies never really went beyond 10%. And so then really in about 2009 and 10, there was this disruptive breakthrough, which was in the form of these perovskite materials, where people were able to go from about 3% to now, which is about 25%. And that's sort of happened. And to put things in perspective, if you compare the perovskite efficiencies to other semiconductor materials, you'll see that this has had an exponential rise. And this is really unprecedented for any material system over years of, I mean, this has never really been observed. And so, and this has really been, this has driven a lot of interest in this material system to understand its properties and to engineer applications based on this. Now, the star that I show is actually close to 30%. This actually refers to a silicon perovskite tandem device that was recently published by, by a group in Germany, where they've shown that you can actually get about near 30% efficiencies if you combine silicon and perovskite. And so that's really being what is the first thing that would probably come to market as people begin to, think about commercializing these devices for photovoltaics. Okay. All right, so what are these perovskites? And so a little bit of technicality, it's any material that has this simple chemical formula of AMX3. And this is a material system that has been around for a very, very long time. And examples are calcium, titanium. These are typically oxide materials or even ceramics and things like this. And so what happened is that people were able to make a hybrid version or a halide version of this, where they were able to replace this A, which was calcium, with an organic cation or even an inorganic like a cesium or a combination of these three. The M, the metal here, the titanium was replaced by a divalent metal, which is lead 2+ or tin or germanium, and there could be other options as well. And the oxygen was replaced by a halide, either iodine, chlorine, or bromine. And so if you mix all of this together and use this formula to predict what it is going to form, which is basically just the ratio of some ionic radii, if you get some value between 0.8 and 1, which means that you've made a perovskite material successfully. And so that's what this perovskite is, and it has some remarkable properties that I want to talk about. Also, just like this is the bulk material or a 3-dimensional material, but there is also a 2-dimensional version of this, which is basically like graphene. You may have heard of graphene. And so it has this layered structure, and that has some interesting properties. And we've done a tremendous amount of work in actually this material because there's much higher stability than the 3D perovskite. Okay, so let's talk a little bit about what makes this material so special. We saw this rise in efficiencies. And so what's so special about them? And so it turns out the first thing is that these are solution process materials. So you can use dirty chemistry, put them in solvents and create very large crystals of this, or make thin films like we did here in this case. And these are some publications, which over the years that have come out on our work. And so you could see that we could actually make these very large grain sizes. You can see them with an optical microscope, and we could get them as large as 1 millimeter. And then if you actually look at the diffraction, you'll see that you get these sharp peaks. And this is typically not what you see for solution-based materials. Typically, you see this broadening, which is representative of defects or disorder in material. And so this is the first time that you could take a solution-based material, spin coat it, and get these peaks, which you would get in semiconductors, which are processed using high temperature. So that's the first thing that was quite amazing about these materials. Now, in addition to this, there are some other properties. For example, one thing is that these are, and I won't go into details, but these are direct bandgap materials. They have very large absorption coefficients, which means that they can absorb sunlight very effectively. And you need a very thin layer to do that. You just need about 500 nanometers of a film, and they should be able to absorb all of the solar flux that is incident on them. Okay. Another thing that is quite nice about these materials is you can tune their color. You can tune the color by changing the chemistry. You can get different sort of concentrations of these different components and change the wavelength at which they absorb. In addition to this, they are very good for transport. For example, the charges that are created when the sun shines on it, these are quite light and they can move around very easily in the lattice. But more importantly, a very important trait in this material, which is different from other semiconductors, is that these are defect tolerant. What I mean by that is that when you create, this material, of course, has a lot of defects, but these defects don't tend to disrupt your charge transport, which helps you in making an efficient device. And so this really helps in getting an efficient device, despite of the fact that there are these defects. And so these carriers live in the material for a very, very long time. And so this is really an important property, I think, that researchers all across the world are trying to understand. Okay. And so another cool thing about this is that all these materials, all these properties, all of these exist in a single material. And that's sort of the magic and the wonder of these halide perovskites. And that's why they've become so interesting semiconductor material for different things. And so in addition to photovoltaic devices, and so here's a chart where we've been, as I said, that we've been focused on these two-dimensional perovskites since about 2015. Is because that we found, in this 2016 seminal paper, that the 2D perovskites are way more stable than the 3D perovskites. This is device which was put under continuous sunlight, and this went on for about 2200 hours and without any degradation. This was another device which was at 65% humidity, and again, you see that these 2D perovskites are way more stable. Now, at that time, the efficiency of these devices was about 12%, which was sort of a record in itself. But now we are at about 18 to 19%. We are about here. And so we have a very nice pathway of going to about 20 and 25%. And this is really important because one of the things that has limited the three-dimensional perovskites, or is limiting them, is their stability. And so our approach to this was that if you can really engineer the stability first, or I guess get the stability first and engineer the efficiency later on, then this could be a very effective pathway for getting something that is translational and get a device that really works. All right. Now, in addition to photovoltaic devices, we have really taken this material as a semiconductor material. We've done a lot of new things with it. So we, of course, use them for photovoltaic devices, but we've also, as I will show you, using this for photocatalysis, for water splitting, and for CO2 reduction. We've made LEDs out of this. We've made electron sources, which is basically Einstein's photoelectric effect. It's a very nice paper that came out recently. We made transistors. We've also worked on radiation detectors because it has lead and all these heavy elements. And finally, we are also trying to engineer quantum defects in it. So really, you can see that this material is a material that can be engineered for all of these different types of applications. So finally, what I would like to do is, I think this is something that we are very excited about, is that we've now taken this material, and these are typically water-soluble materials, right? You put them and they dissolve in water. But we've developed a technology where we can create a barrier on these water-stable or water-dissolvable materials such that it is transparent to the charge, which can go, but it's completely impermeable to the strong electrolytes which are going back through, which means that it does not degrade your perovskite at all. And we can drive bias-free autonomous water splitting to generate hydrogen at about greater than 13%. Okay. And so this is a device which is showing you that it lives so far, and then you get this sudden degradation in this device. And this is because we have a catalyst. We are not experts at making catalysts yet. And so our catalyst degrades. But now this has been improved upon, and we get at least about 10 hours of continuous stable performance. And so we are very excited about this. In fact, something that we are looking to file an IP. In fact, we filed an IP for this and starting a company with this. Finally, if you look at the reported STH, this refers to the solar to hydrogen conversion efficiency. This is kind of where we are, right? And of course, this is in 2021 right now. So, this red dot actually corresponds to that. And so that's where we are. And so we are not very far away from some of the record values, which is 16, 17% for solar to hydrogen, as far as I'm aware of. But we are doing this with perovskite solar cells, which is, so this record actually exists with these 3-5 semiconductors. The cost of 3-5 semiconductors is about $30,000 per meter square, as opposed to perovskites, which is about $20 per meter square. So we are very excited about this. And I feel like this is going to be a very nice, important direction going forward. All right. So with that, I will end, and I would like to thank my group here at Rice University. I'd like to thank Jean-Christophe Blancon, who was with me for about 5 years now, and he's now in Switzerland with the company. Professor Jackie Iucn and Professor Claudine Catan. Claudine is with CNRS, and Professor Iucn is at University of Rennes. Professor Kanadzitis at Northwestern, and Professor Ashraful Alam at Pau University. And so with that, I'll thank the funding which has supported this work. Be happy to take any questions. Okay.
Thank you, Aditya. So I have a question in the chat that says, what makes the Halite perovskite more promising materials than the semiconductors that already show high efficiency and good optoelectronic properties?
Yes, so as I was saying, that these materials are already at the efficiency of semiconductors, right? 25%. And if you look at their fundamental properties, right? So first of all, the cost of these materials is comparable to silicon or even lower than silicon. That's the first thing, if you talk about techno-economics. But then if you look at each property, what is required for a good optoelectronic device, they have all of them, right? Look at transport, you look at the way they absorb light, and you look at the tunability and the band gaps. All of this exists in a single material system. And it's not straightforward to do all of this, say, in other semiconductors without giving a big price for this, right? So that's what makes them really special.
So what about the efficiency expectation of lead-free perovskite materials?
Yeah, so the lead-free perovskite, this is, of course, a debate. I'm not sure if it's a scientific one or a more of a policy one. I think that the tin-based perovskites tend to be a little bit more unstable because the tin likes to convert from a 2+ state to a 4+ state. The chemistry is not as relevant, or I guess not as stable. But I think that there have been a lot of techno-economic evaluations, as far as I know, and talking also with Henry Snaith, who is really the biggest, who made the discovery of these, or the big splash in this community, is that the amount of lead that is there is so small that it's comparable to the background concentrations that we have, right? And so I don't think that this is going to be an issue. Of course, this will need to be recycled and will need to be encapsulated like all other photovoltaic devices. So I think that's what the issue is. And I think at the same time, there is efforts being made to increase the efficiency of lead-free systems like tin-based systems. So these are things that are going on right now.
So tell us a little bit more about the cost difference between these and the normal elements we're using now, and also the processability for the liquid process.
Yeah, so typically the cost estimates for these types, at least the perovskite that has been done, I'm referring to a paper, I think it was in 2018. This was at about $20 per meter square, which is very, very low. Now, I don't know what silicon is, but silicon is quite cheap as well. So these are quite comparable, I would say. But the challenge is that I think that the silicon efficiencies are right now at about 25%, and they are saturated there. I think that the perovskites offer an opportunity to go to about 30%, as I was saying, and that would then offset. That would be really important. And this is combining silicon and perovskites. And so you have these very low cost materials that are compatible with each other. Silicon is, of course, produced and manufactured like we do, and there's a lot of manufacturing that has occurred in China, and so the costs have been coming down. Perovskites, on the other hand, are materials which, as I was saying, is you can take these materials and put them in solution, basically in solvents, and spin them on top of the silicon. And so you get like a film on silicon, which is compatible and works very, very well. And that's sort of the premise. So that's where the community is kind of headed. But in addition to this, perovskites now efficiencies themselves are at 25%. I think the bigger question is going to be about stability, of whether these survive for 20 years. And that there's also a lot of efforts that are being put in this.
Okay, thank you so much.
Yeah.
And the next presentation is going to be performed by Stéphane Cros, is a researcher at the INES CEA, France. And the title is The Efficiency of Perovskite-Based Solar Cells.
You can see my screen?
Yes.
Perfect. I don't have the laser to show you, or whatever. It's not a problem. So I'm Stéphane Cros. I'm working in the French Solar Institute, and my company is CEA. So CA, it is a big research and technology organization in France with many fields of applications. So I remove my mask because, and me personally, I'm working in the research and technology division, which is working notably to renewable energies. Regarding solar applications, we are located in French Alps and in this center in which approximately 400 people are working about a different field of applications in terms of solar energy, photovoltaic or thermal, or integration in the building. So today, I'm working in this laboratory, which is working about tandem solar cells, but not only. It is also, this lab is also working about emerging technologies like perovskite and organics. So my colleague did a very well introduction of perovskite material, so it is perfect. Thank you very much. So as he well described it, it is a unique crystal with, it is a class of materials with possible PV applications, particularly if you have the central cations, which is a lead, and with halide anions coupled with organic or inorganic cations. So it is a class of materials which demonstrated very impressive efficiencies coming from the beginning of 2010, and now we reach more than 25% of efficiency with a single junction. I mean, with only perovskite solar cells. And the solar cells can be coupled with, for example, silicon technologies, not only. And the record with this tandem solar cells is close to 30%. So this objective, this class of materials is very interesting because of fundamental properties like a direct band gap, a low exciton binding energy, and important diffusion length of carriers, and adjustable band gap. By modifying the chemistry of the crystal, you can adjust the band gap or the color. And also, these materials can be processed at very low temperature, and it can be processed with vacuum or liquid process. And this is a big advantage when you want to make low-cost devices, which is very important for PV industry because we need to fight against silicon. It is not a fight, but it is a bit the competitor, considering the industry is mainly in China. And so the cost now of silicon PV industry is very low, which is a very good news considering the cost of PV, of renewable PV electricity. But it is also, it means also it is a challenge to find the new technologies which can be a competitor of current technologies. In this, in our institute, in our lab particularly, we are using perovskite materials in different fields of applications. The first one, it is to make tandem solar cells with silicon and perovskite. So we've chosen two terminal architectures. It means we have a recombination layer at the center of the device. And here you have the stack of what is tandem solar cells. So first the silicon cell, and then the perovskite cells, considering the sun is coming from this, from this side. And this absorber, which is perovskite, is in the range of 400 nanometers, which is very thin. So you can make also, if there is not silicon, semi-transparent solar cells. So we are developing these tandem solar cells. And our objective is also, and it is a specificity of our lab, it is to try to do it with upscalable process, because we want to upscale relatively rapidly these technologies. So we are considering the record, which are very high, but often achieved with small surfaces, which is normal because we need to start with that. We have substrates which are a bit more large, and we are working about the upscale of the process. It is a bit the same with the second application we are doing in this European project, for example. In this project, we are developing perovskite solar cells with flexible substrates. Here it is an example of cells we are fabricating in the lab. And we are also working on modules, because it is possible to make modules using laser scribing. And we are also working on the upscale. For example, these cells are done with a process, the name is spin coating. So you have a drop of the solution and you spin your substrate, but it is not an upscalable process. We want to do it with slot die coating, for example, which is printing techniques for the upscale of the printing. And it is a pretty challenge to achieve the same efficiencies with small substrates and big substrates, considering the crystallization kinetic is a key parameter of this of the efficiency of the perovskite materials, and the crystallization mechanisms are not at all the same with spin coating or slot die coating. So globally in the lab, we achieve very good numbers. For example, 20%, but with 11 square centimeters substrates, which is pretty high. In 2020, it was, we could say, like a world record, considering the combination of surface and efficiency. We also, recently, we did very good numbers with PET-based solar cells. So as I said to you, it is possible to process this material at a low temperature. It means, considering over thin film technologies like CIGS, for example, we are able to use low-cost substrates like PET. So it is a big advantage to be able to process at a low temperature. It is the same advantage than organic PV. And we did also mini modules with this upscalable process. And finally, with very good numbers also. And finally, we are working on the stability. As it has been said by Aditya, the stability of this technology it is a key issue regarding its upscale, because we are very reactive with water, for example. So we need to achieve very good encapsulation process in order to protect against water and oxygen coming from atmosphere. And it is a specificity of our lab. We are working a lot about encapsulation techniques, rigid and flexible. We are also working about the integration of this device in different applications, for example, to make solar fuel, because typically, for example, in this European project, the use of silicon perovskite tandem solar cells could be an advantage because of the high voltage, which is very convenient regarding the fabrication of the solar fuel devices. We are also working on spatial applications, because these materials are very promising regarding the spatial application because of the cost and the weight. And these materials are resistant against particle irradiation which are in the space. So we have specific projects to study this material for spatial applications. And finally, we also use perovskite materials for the integration in for energy harvesting of Internet of Things objects. We have a specific project with this small company in France, in Lyon, Iucn, which is fabricating micro batteries with very specific properties. And we are working on demonstrators which allow to make the energy harvesting of this device, and to make also to build the convenient power management and also the transmission of data, because the properties of the solar cells in low illumination conditions are very good. It is really better than silicon technologies, and it is also better than organic solar cells, because organic solar cells are very good regarding low illumination, but the efficiency is a bit lower. So globally, I think it is the end of my talk. I hope I was not too long. So if you have questions.
That was perfect. Thank you, Stefan. So my first question is, like, how did this perovskite get, like, you know, I know whether discovered is the right question, way of framing it, but When did this all started to replace?
It is pretty funny because it was in labs in charge of the development of dye synthesized solar cells, and they wanted to develop a new oil transport layer, and they wanted to test these materials in combination with dye sensitized nanoporous materials, and they discovered the intrinsic properties of this material by itself. So it was the starting of this technology. So it was a bit chance.
By chance, as always, right? And when did that start?
When?
Yeah.
Approximately 10 years ago.
10 years ago.
Yes.
Okay, so when do you think this perovskite solution is going to be competitive and is going to replace the solutions we have now? What is the time frame for that?
I think it won't be a replacement at the beginning. It is clear we could have different technologies in parallel. Silicon technologies are very well now developed. I think perovskite, the development of perovskite materials is very fast, considering we are now also working about the upscale and of the stability from the beginning of the development. So if we make the comparison with organic photovoltaics, for example, now organic photovoltaics is more mature. It starts to have an industry, and it is a very interesting technology, particularly for new applications. But now we start to see it on true objects. And we have an industry in Europe and in America because it is easier to make plants at a lower cost. So you don't need a big cash to make a big plant in China. I'm sorry to say that. Regarding this perovskite materials, there are different things. The first thing, it is a tandem solar cells. So the combination with silicon. So it means we need to, it will be a bit the prolongation of the silicon industry. And I think, but paradoxically, I think it is a bit, it is more complicated to make tandem solar cells. And probably the single junction technology will be here before, because we can make roll-to-roll processing or pretty simple printing technologies and with relatively simple architectures. And I imagine in 3 years, we could have the first products, but with single junction. But it is only my opinion. It is not the official opinion of my company because I don't.
Sounds good. Let's talk about circularity and how recyclable are, the perovskite materials, combined or not with the silicon. And I know that is a big challenge for the solar panels nowadays.
Yes, it is a big challenge for perovskite because of the presence of lead. And I have to say this lead is not very good because it is not a metal, it is a salt. So the bioassimilation of these materials is easier. But we are, for example, in the Apollo project, which is listed in my talk, we are working about the recycling. And we are now able, we have techniques with a company in Germany, Erturk. We are able to recover the lead from the cells. So, but I think we will have always this issue. So we need to have the control of these solar panels in order to be able to make the recycling of this. So it could be more for solar farms or big installations.
So do you think we will ever surpass the 30%, maybe with some other materials in the future for the efficiency?
Oh, yes, but with tandem, we are at 90.5. So 30%, it is very close. For single junctions, it will be a bit more complicated, but it could happen. Yes, but 30%, it is very close. At a small surface, not a big module.
Perfect. Well, thank you so much for your presentation. Now we're going to go to the next presentation and last for the day. So Louis Dubat from UNEOL is going to present at the title is Urban and Renewable Energy Producers.
Thank you. So Can you hear me? I will share my screen.
Perfect.
Okay. I'd like to put it full screen. We'll do other way. So, hi everyone, and thank you, Mr. Senoric, for being here today. I will introduce you to Uneol, which is quite a young company. It is 7 years old today. And I'm going to introduce you to what is our activity and how we can combine everything that has been said just before with our solution. Today in urban areas, we produce energy through solar panels, and it's quite a known solution. And in the countryside with big wind turbines that have their disadvantages, they make a lot of noise and vibration. And at Uneol, we decided to combine those energy sources and advantages. I will go to the next slide. Everyone can easily know which part of how to install solar panels to make them efficient during summer with the sun inclination and the orientation with the south. But for the wind, it's quite different. It's a more diffused and not very known energy source. But with our expertise in Uneol, we can study the wind potential of any city based on its topography, because a building placed on the top of a hill compared to a building placed in the the bottom of a valley, the first one will be more advantaged by the topography. And of course, if you are close to sea or close to an ocean, you will have more wind potential. And this is what we call at Uneol the wind cadastre. It is made for cities to know which areas are the more, let's say, the more interesting in energy concentration. So to know basically what, if you have a budget to invest in energy transition, what should you focus on first? This so this is a great thing to know, but how to produce energy in urban areas? We developed at Uneol our own wind turbine, which we wanted low tech and made for urban winds. This wind turbine, it's like our almost third generation since the beginning of Uneol. And this wind turbine, we install it on flat top buildings, and we combine it with solar photovoltaic panels, which are like mounted on the top of it. So we combine those two energy sources. This is what it looks like in real life on the right. This is just a module, but we won't install only 2 wind turbines and 15 solar panels at a time. We will make, let's say, a tailored structure based on the building structure with, let's say, 10 or 20 wind turbines, depending on the dimensions and of the wind potential. And this mixed energy platform has another advantage from producing more energy, and during the winter or during the night, we can protect also the buildings, the rooftop surface from the UVs and bad weather. So it can be interesting in summer when it is really hot on this. So we can improve the thermal comfort from the building, consume less AC, and of course we can implement this quite easily. We wanted this wind turbine low tech and also low carbon. We use stainless steel and aluminum that are already recycled to make the carbon weight drop. We are our numbers of gram of CO2 per kilowatt produced are under the ones from the hydroelectric production, under the big wind turbines that you see in countryside, and under the solar panels or the nuclear energy. By 2024 or 2025, we hope to go out of France and to implement our solutions in at least 2 European countries, and maybe we'll see about going to USA after that. Thank you.
Thank you, thank you. So the first question is, what about the noise from the wind turbines?
Of course, because we are making installations on buildings that can be residences or offices. We wanted our wind turbine totally silent, and we managed that. Our wind turbine is based on the Syzygy patent, so it is based on other aerodynamic effects than the big turbines that you see in the countryside. And to be honest, our wind turbine is totally silent. To make it turn, you need wind, and the wind is more noisy than the rotation of our wind turbine.
Is total weight a problem?
Not really, because we are installing an additional structure that is taking its foundation on the building structure. So the weight is not a problem. The forces from the wind that will push the platform up, that is a problem, but we make structure study at every project to make sure the building will not be damaged if there is too much wind on everything.
What about the overall cost of a platform?
It will depend on the surface that we want to install in final. For 1,000 square meters building, it will be like 400,000 euros, or let's say $500,000.
Okay, and what about the overall cost of a wind catastrophe? And can you do it in other areas apart from France?
Yes, we made let's say a funny test with a city in Nepal, just to make sure we were able to do it, as long as we have the topographic data and the weather data. We can do it from France, but for an Australian country or USA, for example. The overall cost will depend on the total surface that we want to study, because we have to modelize and to put everything in our CFD, Computed Fluid Dynamics software. It will depend on the square meters. In the end, it will cost around 50 euros or $60 per square kilometer.
Okay, thank you. Thanks a lot. Okay, so that's it for the 2 parts of the day. 6 amazing presentations. Renaud, thank you so much for having me. I was very, very pleased to see biomimicry, very strong there. And actually, we're going to have Kalima Raskin now from CVOs actually presenting a little bit more about biomimicry. But what I really came out with is that, these technologies are really incipient. Many of them have a lot of potential, but I guess the main challenge, as always, is the industrialization and the commercialization at scale. And I think that's why what we're trying to do at Greentown is, partner more and more with big corporations who can make these pilots happen and potentially bring them to the market in a much faster pace. And I have to say that, a lot of these new technologies also for like photocatalysts for Syzygy, for example, they've been there for a while, but then suddenly, you know, people, they take notice and they start investing because the capital is now there. Syzygy just raised their Series B. I remember them in Houston at the beginning, nobody would take care of them. And I remember Trevor saying, like, I'm never going to get investors in Houston. He had to go to Austin. And suddenly the momentum is here, the capital is here, the corporations and the demand is here. So I think we are really tipping points. And these technologies that seem really early stage are going to get a lot of capital, and pretty soon, you know, they can be deployed to really market scale. So I think we are at this point where everything can be changed in a matter of years. There's a very big, large sense of urgency. And I'm pretty sure that maybe innovations that we can see here now could be fully deployed in a couple of years because of that sense of urgency. So